Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nur Fazlina. My name metric number is C210139. I'm from Group 4 and we're going to explain and present about controller principle. So this is our group member, Muhammad Daniel Hafiz bin Sulaiman, Muhammad Haris bin Zabri, Sir Kemben anak lelaki Ellen Goverdika, myself, and Nohanani Iwani binti Hani Ikmal. So I'm going to intro about PID controller. So professional control is a sort of action utilized in PID controller. The type of feedback control is professional control. It's the most basic kind of closed loop continuous control that is available. While P-only control reduces process variable function, it does not always bring the system to the intent set point. It offers a quicker response time than the majority of other controllers, initially enabling the P-only controller to react a little bit quicker. So this is the P controller output. PI is a feedback control, is PI control, and then the proportionate action result in a quicker response time than integrate only control. The system can be brought back to its set point via PI control, which also prevents the system from oscillating. Although the PI control responds more quickly than integer-only control, it still reacts up to 50% more slowly than P-only control. So this is the PI controller output. And lastly, for PID control, a combination of three types of control approach is known as proportional integral derivative control. Because PID control incorporates the benefit of each type of control, it is the most often utilized type of control. This includes a speedier response time due to the P-only control and a smaller offset due to the employment of both combined derivative and integral controller. So this is the PID controller output.
My name is Nurhanani Iwani binti Hani Ikmal. Matrix number is 810020. The closed loop system with PID controller. The first component is step block, sum block. This is the PID controller. The parameters is proportional 3, integral is 2, and derivative is 0.1. Apply, OK. Next, the transfer function, the numerator coefficient is 3, denominator coefficient, apply, OK. This is the scope. I will run it, and the waveform is, the blue line is the time response, and it shows the overshoot here. The yellow line is the step input.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Daniel Hafiz bin Sulaiman, DE210044. Okay, I will start my presentation with the simulation. So, for the first thing that I want to show is for the open loop PID controller. Okay, this is for the open loop system. When we open loop, it will not connected to the PID. So we just run the simulation, and we can see here this is the graph for the open loop system. So we know that if we make it as open loop system, open loop is a motion system that there is no position feedback of a moving object. And for the closed loop system, it means that there is some input, there's feedback to the motion controller of a system. So that's why open loop and closed loop, the graph will be different. For the open loop, the graph will be up, and for the closed loop, it will have peak time, overshoot, and also the steady state error. Okay, we will go to the closed loop simulation. Okay, I will continue for the simulation PID controller. So today I will explain for the P and PI controller. For P controller, this is our transfer function, and this is our P controller. So we just enter the number for P controller, open the block parameter, and here is the block parameter. So we just select the P controller, insert the proportional for 3, and we hit OK. After that, we just run the simulation, and it will show this graph. After it show for the graph, we can see that the overshoot slightly higher, so we have to tune it. The ways to tune it is open the block parameter and hit the tune button. After we hit the tune button, it will show this, and we can slide the response time to choose the best graph that we can get, the best tune that we can get. Okay, this is our parameter that we have tuned, and from here we can see the parameter. Okay, this is the parameter. We can see here the block that we entered earlier is 3, and the tune version is 2.4. Okay, after that, to apply this number inside the block parameter, we just hit the update block. After we update the block, our block parameter will show the value inside the block parameter. Okay, this is the tune version of the block parameter for P controller. After that, I will continue for the PI controller. Okay, we just enter the number inside the PI controller. Okay, so for the block parameter, we'll just switch to PI controller. Proportional will be set to 3, integral to 2. After we hit enter, here, after we hit the run, it will show this graph. If you see this graph, it still have many overshoot. So how does we have to tune this? So we just open back the PI controller, and from the block parameter we just hit the tune. After we hit tune, it will show the PID tuner. Okay, we can see here the graph will have a better settling time, and also the overshoot not too high, and the peak time also from here. So from here we can see we can slide the response time for slightly better, and we will see the parameter. Okay, here it will show the tune parameter, P how much, I how much, it will give the answer. After that, we'll just have to update the block to apply the number inside the block parameter, which is here. Okay, we can see here, we will hit the update block. Okay, so it will update the block, and also it will and insert the tune number inside the block parameter. Okay, that's all for me. Thank you.
So my name is Muhammad Haris bin Zamri and my number matrix is DE210053. Alright, so for this is a PID controller circuit that I will present, which is this is 3, 2, 0, and 0.1, which is a value for PID, which is we use step, sum, PID controller, transfer function block, and scope, which is this is the value that we use at equation that we use at transfer function block, which is a 3 per s square plus 2s minus 3. After we press the run, this waveform will get a scope, which is this is a circuit closed loop. Okay, and after that we get this, you can see at the PID controller, which is the value that we put, and here filter coefficient is 100, and this is the equation for PID, and you have to you press tune, then it will get you this graph. This is a graph of step, this graph at scope, and this is graph at PID controller, which is this is a controller parameter that we use put at PID, and you can see this is a block, this is block, because this you can see 7.83 this it becomes smooth and stable, and then this is 2.549, this is one, it becomes smooth and stable. Alright, I will show you at my MATLAB. Alright, so this is the basically circuit that I say closed loop PID controller, and this is the waveform that I show to you. After that, we press this run button. You press this scope, and it will get you this waveform. And you can press this PID controller, and it will get you this. So you can put the value for P, I, D, and this is filter coefficient and equation that I said that apply at this value. And you press this tune, and it will get you this waveform, and you press the show parameter 2, it will show you the value for this all of at here. And for your information that you can modify this, which you press the cursor to the faster and robust, and we will get you the the value for the waveform new, stable and smooth, more stable and smooth. Right, you press the update block. Alright, so as you can see, after you press the parameter block, you can see this value PID is already adjusted to become the more improved and more stable. For this, you can see settling times it become the same and same, stable. It is the same because of why it's same. You can see this, and the scope I say it already has the same value, same waveform like this PID controller, which is I say it 0.0387, which is at here, maybe at here, nearly at here, which is it become and in one line. And this block parameter also change. You can see this change for the value, for the value uh, yang sesuai untuk for this this PID controller. Alright, so for the conclusion for this PID controller is to improve the continuously waveform, which adjustable this value PID.
Conclusion: positive outcomes were obtained from the simulation using the MATLAB Simulink software in the closed loop and open loop system. While closed loop system employ the post-possession data for the accurate positioning and open loop control functions without positioning feedback. The system response was overshoot despite the big reduction in driver time. Steady state inaccuracy is addressed by the PI controller, although the stability the stability and reaction time are adversely affected. The PID controller provides the short reaction time, little steady state error, minimal steady state error, and optimum control dynamics. It has a wide range of applications for higher order processes with numerous energies stored storages and combines all the advantages of PI controller with the exclusions of the derivative gain component. Overall, the control dynamic stability and various energy storage, the PID controller is a better option. That is all from me. Thank you very much.